Hello, this is Mike, and I'd like to talk about the some tough topics using Mathematica 8 to tackle the actuarial problems, and this is video number 4, and I would like to talk about topics such as Bayesian estimate, Bowman credibility, etc. So we'll start looking at an example, and you don't have to read it really too carefully because the point here is not getting the exact right numerical answer, but rather understanding how to apply the method using a powerful software tool. So we're given a very standard credibility problem, and you can pause the video now to read through the question. But first, how we tackle this problem is we're using the Bayesian method, where you have to calculate a posterior density, and if you really don't like that terminology because it's a little pedantic sometimes, but essentially what it is it integrates over the possible interval and calculates a joint distribution of multiple random variables, and in this case there's only one, but here is the posterior density, and having that we can include that in a final answer, which this part, which 0.9 plus q, is merely the expected value of the number of claims. You can calculate it from this small table, and times the posterior density, and that shall give you the final answer, which is the x3 conditioned on the previous 2 years having 2 claims each. Okay, so now moving on to Bowman credibility, I've prepared another example here. I may blow up just a little bit for you to read, and you can pause it now. And after you finish reading the problem, you will notice that it's a fairly verbal question, but it wants a numerical answer, and more than likely a lot of the most important information was really buried in the 5 conditions here. So you first have to realize that a collection of such individuals in this book of business is really essentially a collection of Bernoullis here. So, and to tackle Bernoulli, we know that individually the variance is theta times 1 minus theta, and the mean is theta. So knowing that, what is A in Bowman credibility, which is the variance of hypothetical mean? So therefore the mean of individually variance would be 0.01, which is given by condition 5 here. And I've listed the formula here in the comment. V, which is the EPV, or the expected value of process variance, is merely a computation of 0.1. Now this 0.1, it's coming from condition 4, which is the overall, and minus 0.1 squared times 0.01. And these are really the calculation of E theta minus E theta squared. And E theta squared can be calculated from E theta and variance of the theta, which are both given in condition 4 and 5. So there's really a lot going on. And when you're reading the problem, if you can't figure out V and A from condition 4 and 5, there's really not too much for you left to do, because the rest is really standard. It's n equals to 10. Because you're given the past experience of 10 years, and Z is really n divided by n plus V over A. And since we'll ask the next 5 years, the exposure unit is not exactly 1, so we times our Bowman estimate by 5. You can see I left some of my other scribbles here, and you can see what kind of function I normally use under the category of Bowman credibility problems. I do a lot of integration to find moments of symbolic densities, and I use the numerical integration to find integrals, and I use numerical solve utility to solve equations, and I use it as some really pointless calculations, but it just saves a little time. And for non-parametric, you can do that similarly, since it's all data. And for semi-parametric, I just want to mention really quickly, I have another example here where you have 2 classes of observance, and in this case they're vehicles and they have claims, and it's non-uniform because you have 2 classes where you have 3 years of experience of observations for one class and 2 years for the other. In this case like this, you have to use that really notorious formula for variance of hypothetical mean, but all you need to do really is a really good programming practice where you specify M1 and M2 and you write out all the variables and you write out the formula, you can plug them in. So if you need to change for one for your particular project or problem, this code is really reusable. So I think that's really one fantastic thing about using Mathematica. And we'll talk about simulation in the next video.